Hello everyone, welcome to week 3 tutorial. In this recording, I will repeat the tutorial example we have in week 3 class last Thursday so that you have better idea about the solution. And let's have a look on the tutorial questions. So in this class example for week 3, it is required to calculate the maximum compressive capacity in asterisk for a 6-meter high cantilever column from built-up cross-section. This built-up cross-section consists of 4 equal angles, 100 by 100 by 12 millimeter, as shown in this figure here. And if the buckling length or the effective length for the column is 2.2 times 6 meter, because it is cantilever column. So if this 6 meter, so the buckling length actually is this length, which is 2.2 times 6 meter. So the effective length or the buckling length already given to us as 2.2 times 6, and the yield strength of the steel is 300 megapascal, and we assume that the lacing element has enough capacity during the column loading. So the dimension of this column are here. The distance between the CG of, let's make it clearer. So this is IB, angle equal angle 1, equal angle 2, and 3, and 4. The distance between the centroid of this angle line to this angle line is 500 millimeter, and also in the other direction from the centroid here to the centroid here is 500 millimeter as well. And here is our section. Section is equal angle 100 by 100 by 12 millimeter. Okay, this is the plan view. So if we want to allocate the axis, here is our X and Y axis for the whole section. So this is the CG, this is our X axis, this is our Y axis. So this plan view. For the elevation view, we have the angles, and the angles are connected together with the lacing elements here. This angle of the lacing element is 30 degree, so this means this also 30 degree and this also 30 degree. And this is our angle, equal angle 100 by 100 by 12. So these are the given information about the built-up section. So now let's start the solution of this section. So to find n asterisk, we need to find two capacities for the member, which because n asterisk should be less than or equal to phi ns and phi nc. Phi ns is the section or the nominal section capacity of the member, and phi nc is the nominal member capacity of the member, where section capacity is concerned about local buckling or local behavior of the column, and the member capacity is considering the global buckling behavior of the column. Okay, so this the two capacities. So we need to find phi in S, phi in C, and N asterisk will be the smallest of these two. So let's start with the nominal section capacity or section 6.2 of the Australian Standard 4100. So from 6.2, NS, the section capacity equal to KF form factor times AN times F yield. AN, if KF is the form factor, AN is the net cross section area, and F yield is the yield strength of steel. So the net cross section area AN will be equal to A gross assumption and will be equal to 4 times area of one equal angle. From the table below here, for the equal angle tables, so we have 100 by 100 by 12 equal angle. The cross section area for this section is 2260. So we have 4 angles times 2260. So the total area is 9040 millimeters square. And for the form factor, also from the tables, for this section, 100 by 100 by 12, the form factor Kf equal to 1 here. So Kf equal to 1 from the one steel structure steel tables. So now the section capacity will be 1 times 9040, the area, times 300, the yield strength in Newton by millimeter squared. So the load or the section capacity is 2.712 times 10 to the power 6 Newton, which is equal to 712 kilonewton. And as you know, to convert from Newton to kilonewton, we need to divide by 1000. Okay, so this for the section capacity of this member. Let's now go to the nominal member capacity or the member capacity of this member. So for the nominal member capacity, according to section 3 of the standard 4100, the member capacity for the whole member or for the member as whole equal to NC equal to alpha C times NS and should be less than NS. This is the formula for built up section or normal hot rolled section, like the universal column section or any other hot rolled section. So NC equal to alpha C times NS and should be no more than NS. So we know already NS, which is from the previous step to 712 kilonewton. So now we need to find alpha C. So this is a cross section we have now. So we have the 4 corner angles, and this is the CG of the whole section. And the CG of each angle is 250 from the center of the centroid for the whole section. So to find alpha C, we need to know lambda n and alpha b for the whole section. So our first step now is to find lambda n, the modified slenderness ratio, which equal to L effective divided by R multiplied by rho KF multiplied by F yield divided by 250. So we need to find this value, the slenderness ratio. So this is the first requirement. So to find R equal to I divided by A under the square root. So we need to find firstly Ixx for this built up section. So for Ix will be equal to the inertia of one angle multiplied by 4. The inertia of one angle will equal to the inertia about its own axis, In, plus the area of the angle times the distance from the center of the angle or the CG of the angle to the CG of the whole section. We can call it D or A. D here is this distance in total is 500 millimeter. So D equal to 250 millimeter based on the geometry we have. So this formula comes from the general formula of I about x-axis equal to the inertia about the local axis plus area times d squared. So because we have four angles, so this is 4 here. Four angles. So the inertia of the angle IN from the table 2.08 times 10 to the power 6. This from the equal angle table here. In equal to I polar, IB equal to 2.08 times 10 to the power 6 millimeter to the power 4. The area for one angle is 2260. We used it before. So this for one equal angle from the capacity table. So now Ix for the whole section equal to 4 angles, 2.08 times 10 to the power 6 plus the area 2260 times 250 squared. So the inertia for the whole section is 5.7 times 10 to the power 8. So after we know I for the whole section, or I cross, sorry, Ix for the whole section, and we know already A gross. So R, and in this section, Rx and Ry are equal because it is symmetric section. So Rx equal to Ry equal to root the inertia we got 5.7 times 10 to the power 8 divided by the area 9040, which give us a radius of gyration of 252. If we know the radius of gyration, so lambda n for the whole or lambda e for the whole member equal to the length or the buckling length 2.2 times 6000 millimeter times L divided by R. So this gives us a modified slenderness ratio of 52.4. So this for the whole member. That's why we call it lambda n or lambda e for the member. The second step is to find for the component. So our main component for this column is the angles. So our main component is the equal angle, 100 by 100 by 12. So we need to check the cylinderness or to find the slenderness ratio for the equal angle. From the geometry, we need to find the buckling length or the unsupported length for the angle, which is this part. So we need to find L effective for the component, which is equal to 577 millimeters. How we got this value? If we take this triangle outside, so this a right angle, this is 30°. So we know this distance as 500 millimeter. So now we can know half of this one. Let's call it y. So y will be equal to 510 30, which is equal to 288.7 millimeter. So L effective for the component will equal to 2 times this number, which give us a value of almost 577 millimeter as our buckling length for the component. So the slenderness for the component equal to the effective length of the component over r y of the component. So 577 over 19.5 equal to 30. 19.5 is the radius of gyration for the equal angle, 100 by 100 by 12. And we take ry because this is the critical r for the angle. So from standard, lambda or le over r for the component C should be less than two values, 50 and 0.6, the slenderness ratio of the member. So we got this value as 0.6 times 52.4 because we already got this value as 52.4. So L buckling, L effective for the component should be less than or equal to the smallest of these two values. So this value is 50. This value is 31.44. So based on our calculation, 30, the buckling or the slenderness ratio for the component is less than 31.44. So no problem with the buckling of the main component. So this means that no buckling will happen for the main component. Okay, because 30 less than 31.44. Here is the values for R for the angle. Here is Rx, here is Ry. So Rx 38.2, Ry is 19.5. That is why R equal to Ry equal to 19.5 millimeter. So after we got . the value for the slenderness ratio for the component, and we check everything is okay. So now we can find lambda n. So lambda n equal to LE divided by R times KF times root F yield over 250. So L effective is 2.2 times 6,000. R equal to 252. And the form factor is 1. So we got lambda n for the member equal to 57.4. So using this value, we can go to table 6.3.3a to find alpha b, because we need also alpha b. Alpha b from this table equal to zero point 0.5 because we don't have equal angle here. So alpha b equal to 4.5. Then we can go to table 6.3.3c using the two values we have, lambda n equal to 57.4 and alpha b equal to 0.5. So if we go down, so for lambda n and alpha b 0.5, we can got that lambda c equal to 0.762. Okay, so if we go to the table 6.3.3, we know that lambda n in between, somewhere in between here, which is 57.4. So, and here is alpha b equal to 0.5. So our value will be something in between these two values. So using interpolation, you can find the value of lambda alpha c equal to 0.762. So if we have lambda n equal to 55, this give us 0.778 of alpha c. And if we have 60, this give us 0.746. So if we have 57.4, we need our alpha c value. So if we apply the interpolation here, so alpha c minus 778 divided by 0.746 minus 0.778 equal to 57.4 minus 55 over 60 over 55. So we have alpha c minus 0.778 divided by 0.746 minus 0.778 equal to 57.4 minus 55 divided by 60 minus 55. This will give us the value of alpha c equal to 0.762. Okay, so this is our alpha c. If we know alpha c, so we can apply in the formula of member capacity. So 0.6762 times our NS to 712 give us a value of 2056 kilonewton. Okay, so as we know, N asterisk should be less than phi ns and phi nc. So N asterisk would be the lesser between phi ns and phi nc. And as we know, ns is 2712, nc is 266. So this means that the smallest is, or the lesser is phi nc. So phi for steel members is zero point 0.9, and we know nc as 2066. So this means that the maximum compressive capacity of this member in asterisk equal to 1860 kilonewton. This is the maximum compressive or maximum axial compression can be applied to this member. Okay, so this is the requirement and this is the final step of the solution. And if you have any question, please let me know. Thank you.